Hi, my name is Brianna. I was being recorded for Group 1 with the lab of the thermocouple time constant. So coming to this, I didn't even know what a thermocouple was. So of course I did Google and got a simple answer of a sensor used to measure temperature. And it also reacts to temperature change more whenever it's placed in water, which is pretty cool. So since we didn't have a leader for this one, I wanted to do the experimental procedure just to kind of reiterate it. It was really simple. We just went in there, turned on the stuff, and got a beaker, because we did two different experiments. I had the bowl in water, so you got the beaker filled with hot water, set it on a hot plate, and let it start to boil. Then you would run the program, and then stick the thermocouple as soon as you could in it without touching the bottom, and kind of hold it for a little bit for it to heat up, and then pull it out. And then whenever you would pull it out, you would immediately wipe off the water, so the water couldn't affect the temperature change as it would start to cool off. And then you would shut down the experiment. So then I wanted to give the definition of the thermal time constant. So it's a quantitative way to express how fast or slow a sensor responds to a change in environment. And then the equation they gave us in the instructions was time equals to negative tau, which tau is your time constant, and then ln of your normalized temperature equation. So then this is raw data for both of our experiments. I did see the heat or the boiling water had almost an instantaneous temperature change versus the cooling water had took longer to cool down. And then the time constant formula. This is just how I got the time constant formula. So you would plot the log of the normalized temperature versus the time. Then you would take -1 over the slope, which will give you your time constant. And of course, if your slope was negative or positive, you would just do 1 over that, not negative. So then to manually calculate it, you would do the difference in the temperature change, and then multiply it by 63.21%, which by that time, that's how long it took for 63% of your temperature to change. And then you would see how long it took, just kind of like whatever it correlates to. So then I had the boiling, of course, so the boiling, this was the insertion. Yes. So this is the time of versus the log of the normalized temperature. And then it wanted us to find the tau of the curve fit, which you can see here in the experimental. They did vary in every single one that I did. The curve fit tended to be either a little bit lower or a lot higher. I'm not really sure why. But then this was the removal. It took a lot longer, of course, for it to cool down than for it to heat up. So that's why the curve fit had a lot larger of a time constant. But the experimental was a lot more accurate value when compared to the overall data curve. The steady state temperature was about 38 degrees Celsius. I don't know, we didn't fully get there because we stopped the data recording. But it did take almost 200 seconds to get close to that after removal. So then here was the ice water. As you see, it wasn't as much of a change. So it took a bit longer, so the time constant was a bit higher than the boiling water. And then for the removal, you see the time constant was a lot higher. Even the experimental, they did vary a lot. But for this one, the steady state temperature was 50 degrees Celsius, and it took about 121 seconds after removal to reach that, which was a lot less than the boiling water. So then I wanted us to graph the time versus the normalized temperature, and then so it's the heating versus the cooling. This is the insertion, and then this is the removal of the cooling and the air heating. And then at the end, it wanted us to download 4 different sets of data from the same experiment, but I could only find 2 of the removal from the boiling water. They were pretty close in time constants. On the next slide. And it also wanted us to do the mean and the standard deviation. And then the mean of this one was 87.4 or 14 degrees Celsius, and then for this one it was 86.6 now, so it wasn't much of a difference. But the time constants were pretty similar. And then my conclusions. So the time constant is defined as the time required by a sensor to reach 63.2% of a step change in temperature under the specified set of conditions. And then learn this, it also helps you pick which sensor to use. And then the response of the sensor to a sudden change in the surrounding temperature is always exponential. And the time constants may vary significantly between the curve fit and exponential values due to the slope of the data and range of the values plotted.